Welcome folks, we would like to give you a new tutorial on ORCAD capture software. And ORCAD capture software is electronic design aid software that is mostly used by application engineers. So what does that mean is that this particular software is used by the engineers who design the applications, electrical engineers of course. For example, motherboards for PCs, smartphones, Nintendos, power supplies, motor drives, toys. It is basically how to use the electronic circuits or what they are used for. It is the applications that are used. So ORCAD capture basically will enable application engineers and PCB designers to verify that the application, the circuits, the electronic circuits work properly in simulation, and then it will also provide a tool to convert those components into the PCB, the printed circuit board. And basically the application engineers can send this design into the house, the manufacturing house or the assembler, to put those parts together, and then they ship it back to them. And ideally, if the design is done correctly, that this particular application should work according to the specs. Basically, ORCAD is used to design electronic circuits, and you will be able to dump this electronic circuit on printed circuit board, which is the PCB. So in this tutorial, we're going to learn very simple techniques for circuit simulations or circuit analysis. We're going to learn 3 types of analysis. The first one is called DC sweep, and then we're going to learn the small signal AC analysis, and then we're going to learn the time domain transient analysis. And basically those are analysis techniques that will simulate the circuit that we're trying to design to verify that the circuit works accordingly or properly. We're going to use simple electric circuits like voltage divider and RC circuits, but we would like to show you how is the different analysis that we can use to verify the circuit behavior. And in later tutorials that we will learn how to use some of those electronic circuitries to verify that they work according to the design specs and so forth. Now this tutorial is basically designed for my students at Washington State University, but people from different areas who would like to learn about ORCAD capture tool, they can look into this video on my channel, on YouTube. So you are welcome to do so. I'm going to show you how you can download the free version of ORCAD. So basically, if you go to Google, just type on Google ORCAD download and click on, and here you have different options. I mean, this is basically in today's search. In fact, let's do that today. So we're going to click on it. And now when you come in, you have different versions. So now we have the new light version, which is the 17.2. If you can download that, you can. But when you click here, ORCAD will not allow you to download it right away. You have to fill in a form. So you have to write your name, your last name. Make sure that your email is correctly. So write your email, because they will email you the license through email. So you have to download it through email to get the free license. Then you should, if you wanted to write your university or company that you work on and so forth. But when you wanted to download it, if you're going to use 17.2, that will be basically 64-bit. And then make sure you click on the first one, which basically going to say all products download. Or if you want to use the 16.6, which is the version that they have, so you can use this one. You can say ORCAD 16.6 Lite software, all products, and then it's going to be downloaded. I'm not sure if they will be able to mail you the DVD. You can try, but I mean, for me it's much faster to just download it. So fill in this form and submit, and you should receive an email shortly and then you can download your light version via email, and you should be able to install and run ORCAD light version very easily. As soon as you do that and you install the software, all what you do is you come to the start menu here, and then you're gonna have this icon that's called ORCAD Capture CIS Lite. If you can't find it here, you can go under the main menu and look for Cadence, and then ORCAD Lite 16.6, that's the one I have, and then you can click on the ORCAD Capture CIS Lite. Either one will work, so I'm gonna click here, and now you gonna have the first GUI have been shown to you, the graphical user interface. And what I'm gonna do is I'm gonna come to File, and I'm gonna create a new project. So go to File, and then click on New Project, and here we're gonna use Analog Mixed Signal AD. Basically what we're gonna do is we're gonna run circuit simulation only. We will not do board wizard, we will not design the PCB, printed circuit board, we will not do that. We will only simulate the circuits, so we're gonna use analog or mixed AD circuits, and then we're gonna give it a name. So we're gonna say that part 1, you can give it any name, it doesn't matter. I'm gonna call it part 1, that stands for this tutorial, and then we're gonna click OK. So this is gonna be stored in this directory here. I don't care where you want to store it, but make sure you store it here. This is the default, I believe, but you can change it if you want. It's not a big deal. Click OK, and when you come here, say that create blank project. I'm not gonna board or create a project based on existing project. It will be a new blank project. That's what I'm gonna do, and then I'm gonna say OK. So this basically here is a schematic window. Basically we will be able to draw the circuit on this schematic. Now you can have too many options to go through, but we will not go through those in this tutorial. We basically going to show you the basic things that you need to do to run those 3 simulations. So the first circuit we're gonna run into is we're gonna use a voltage divider, and we're gonna apply a DC voltage source, but we will vary the value of this DC voltage source. So this is called DC analysis or DC sweep. I will basically vary the voltage, the DC voltage, from some initial value to some final value with some incremental steps. So it's a very simple circuit. We're going to use 3 resistors in series, and we will have a voltage divider circuit. So you need to come to this portion here where it says place part. Now when you click on this, you need to add libraries because I don't have any parts here. Now keep in mind that libraries are the core or the heart of any of those circuit simulation software. Almost all software you're going to use, they should have libraries you have to port and use. And there's thousands and thousands and thousands of different parts. So those companies have been investing a lot of time to develop those libraries, and they usually communicate with the other companies who manufacture their circuitries, and they come up with those different models for those parts that we use. So here to add a library, we're gonna come here where it says libraries and click under this icon. So let's go back again and tell you what we did. We came here and it says place part. This here will open up. I have to add a library. So to add a library, I'm going to click on this one, and there is some existing libraries that we need. There's 3 libraries I'm going to add on this tutorial. The first one is called source. So look under those libraries. It's under the PSPICE. PSPICE is the standard for circuit simulation tools that we use. So look under source, click on it, say open. So it is added. And this basically will have things like the different voltage sources and current sources we can use to simulate our circuits. So that's the first library we will use here. It's called source. The second one, we're going to call it eval. Eval is a very old library that have been used. In fact, that I even learned eval when I was an undergrad back in the 80s with the very, very old versions of PSPICE. Very old versions, not as user-friendly as those ones. So eval is one of the old standard libraries that are used, especially in educational purposes. So we're going to add this eval library, and now we have the eval. So eval will have simple components like simple transistors and diodes and op amps and all that, and simple logic circuits and so forth. We will not use any of those in this particular tutorial, but you will be able to use them later on in the following tutorials. The next library we need is what we call analog. So analog library is basically the one that will have the resistors and the capacitors and the inductors and so forth. So in order for us to look for a part, you can select the library you want it, or I can select all of them, and now I can choose any of those components I want. So by selecting all of them, now I can choose any of the parts in any of those libraries. The first thing I would like to place into the schematic is the DC voltage source. So I will write VDC here as a search in the search field here, and then it will show me VDC source. Basically says that the VDC is located in the source library. So I'm going to click on it or double click on it, and I will see it here, and I can place it in the schematic window over here. So I will place this particular voltage source over here, and let's zoom in a little bit. So here I have it, and then I'm gonna hit escape. So by hitting escape, you can see that I don't have to add more voltage sources to it. So what I will do now, the voltage source is called V1, and the value is 0 volts. So I can give it any value like 1 volt if I want it, or 10 volts. So let's give it 1 volt. So 1 VDC, or you can write 1, and that's good enough. That's the way I like to do it. So this is 1 volt, or let's do 1 V, and that stands for 1 volt. So we know now this voltage source has 1 volt. And then we're gonna add 3 resistors in series. So I'm gonna write R here in the search field, R, so it shows me R analog. So I'm gonna double click on it. So this is the first resistor. I'm gonna place it here and then here. So those 2 in series. And the third one, I'm gonna rotate it 3 times like that, and I'm gonna place it here. So, and then I'm gonna hit on escape. So I will have 3 resistors, R1, R2, and R3 connected. They're going to be connected in series. I would like to keep the R1 to be 1K, the R2 to be 2K, and R3 we can make it 3K. As shown here. And now I'm going to connect the entire circuit in series. So I will come here, and I will see where it says place a wire. I'm going to click on it, and I'm going to come to this particular end of the V1, and I'm going to connect it here, and then I'm going to come to this one, and I'm going to connect it there, which basically means this end of R1 to R2. This end of R2 will be connected to R3. Now you can connect the 2 other end of R3 to the voltage source like this, and I don't like to do this one. I like to do it different. So what I will do is, let's do Control Z, basically undo. What I like to do is I would like to connect this end to ground and this end to ground, and that basically means it's the same thing. You must include a ground in your circuit. There is no way out. So we're gonna come here, and where we have the ground, place ground. So we're gonna have a new window to use. What I'm gonna do is, I would like to use this one over here where it says Z cap sim. So this is the one I'm gonna use. So I'm gonna connect the ground here and the ground here. So that basically means that this node is connected to this node connected to ground. So ORCAD will understand that those two are the same node, right? They are the ground. So now we have defined the simple circuit. Now what we are interested in is to define the simulation, how we are going to simulate the circuit. So I'm gonna come here where we say that place a new simulation. So you're gonna enter a new simulation here, and then you're gonna give it a name. So we can say sim DC, and we will say create. So at the bottom of the window in the PC, you're gonna have a new application or a new window is created. Click on it. This basically will tell you that what kind of simulation we're gonna have. The default is a time domain, which is a transient simulation. I'm gonna change that and I'm gonna make it a DC sweep. So when we do DC sweep, we going to enter some values. The first thing is what's the sweep variable. So we're gonna say it's a voltage source. I'm going to change this voltage source. You can have different types of DC sweeps. You can have current source, you can have global parameter, you can have a model parameter, or you can sweep the temperature. By changing the temperature, how is the circuit gonna behave? In any case, we're gonna do a voltage source sweep. So it says voltage source, enter the name, and I'm gonna do V1. That's basically says that this voltage source is the one that we're gonna sweep, and the type of sweep gonna be linear. I'm not gonna do logarithmic, I'm gonna do linear. The start value gonna be from -10, and the end value gonna be 10, and the increment as we go from -10 volts to +10 volts, the increment going to be 0.1. So this is called a DC sweep, where you basically going to change the value of V1 from -10 to +10. We're gonna say apply. Okay. So now what we're gonna do is we would like to know what we're gonna do with, or what we would like to measure with this kind of DC sweep. So by changing V1, what we would like to do. So I wanted to measure the output voltage across R3. So the way to do that is basically to come here and to click on this one. This is basically a probe. A probe is similar to the concept of oscilloscope. So you have a probe added to this end. So I'm gonna measure the voltage at this end in reference to ground, and that basically will be a probe. Right? So what's the voltage at this end? And then I would like to measure the voltage across R2. So we can do that by clicking on this probe. This is called differential marker or differential probe. Basically the differential probe will measure the voltage from this end to that end. So this is the plus and this is the minus. So you're going to measure it from here to here. So you should have a different value for this voltage and a different value of this voltage. I think that's all what we have. So let's save the circuit. We saved everything. I'm gonna click on escape to cancel that probe marker, and to run the simulation, all what I have to do is come here and say run PSPICE. Now PSPICE is the circuit simulation that will run the simulation. The way the PC going to evaluate the circuit is called PSPICE. This is called the circuit schematic. So that's what we have here. So let's run PSPICE. So we're gonna click here, and this is a very quick simulation. So it's already completed, so there is no errors whatsoever. So you can see that the red color will be the voltage over here and the green color will be the voltage over here. We're gonna come at the bottom here and we're gonna click on it. Now this is the simulation window or the PSPICE window where it will show us the results. Now the green is basically the voltage across R3, the 3 volts, and that is clear that it's going to go from -5 to +5, while the other one going to go from roughly 3.6 more or less to +3.6, and it's linear because this is the voltage across the 2K ohm resistor. Now this is a very simple circuit, and it's clear that it's a linear relationship between the voltage and the resistor, right? By increasing the voltage, Vin, Vout will increase linearly. But here for a given voltage, for example V1, if V1 equal 3 volts, you know that the voltage across the two resistor going to roughly be this value, where we can have a cursor. So here is the cursor. So let's say that when we have 2 volts, so at 2 volts Vn, VR3 going to be 1 volt, and VR2 going to be 0.67 volts, or 67 millivolts, more or less, right? So this is roughly about 2/3 of a volt. This is about 1 volt, which is half, when Vi equal 2 volt. When Vi equal 3 volts, which is somewhere in here, right? So we know that the green gonna be 1.5 volts, and the red, which is V2, gonna be roughly around 1 volt. So that's what we have. In any case, what this shows you here is a graph of what's the input voltage is versus what's the measured voltages. We measured the voltage V3 and the voltage across the resistor R2. So we're gonna close this one, I don't need it. So we're gonna run a different kind of circuit simulation now, and we going to create an RC circuit and do AC sweep, small signal AC sweep. So let's save this one, and then let's go to the project menu over here, and over here I have the schematics. So I created a page called page 1. So now we can create another page, new page, and we're gonna call it page 2. But here page 2 will not have any relationship to page 1. I'm gonna delete those props because I don't need them. Well, even though they are under the same project and everything is related, but there is no link of whatever happening on page 1 to whatever happens on page 2. You can link them. In fact, that's one of the things that we are interested in when we come to ORCAD, is to use something we call hierarchical design, or the hierarchy of the design, where you can design module and you use this module to define another module and another module and another module and so on. All what I'm going to do here is I'm going to design a new circuit on the new page. So what I'm going to do is I'm going to add a part. So I will come here where I have the library of adding a part, and I'm going to add VAC. VAC is basically the small signal AC analysis that is used for AC analysis, and we will keep this voltage to be 1 volt. So it have 1 volt AC, 0 volt DC, and basically this is called or used for the frequency response. So we're gonna apply this voltage source, and then we're gonna connect a resistor in series with it. So we're gonna say R, and this resistor gonna be 1K, and then we're gonna have a capacitor C, and I'm gonna click on R, which means rotate 3 times, and now we're gonna have this capacitor that's called C1 and has a value of 1 nano. So to add a capacitor, basically you come in here to the search part over here, and you gonna write a C, and right away under the analog library you're gonna have C analog, right? And then you bring it over here by double clicking. It comes over here, and then you click on R 3 times and you place it over here. So now all what we have to do is connect those elements together. So I'm gonna go from the voltage source into the resistor to place a wire, and then from the resistor to the capacitor, right? So you make sure that you add place a wire, which is different than those ones, right? And this is a bus which is totally different. So the wire will be the thin icon over here. And then we're going to add the grounds. So the ground we're going to use is the cap sim, and then we're going to have a ground here and the ground here. And finally, the value of the capacitor, I'm going to make it around 3 micro. Farad. So we're going to have 3U stands for 3 micro. Click OK. And basically the circuit diagram have ended. It is very simple for us to draw circuits in ORCAD. Now we're going to define a new simulation, or we can modify the old simulation. Remember, the old simulation was sim1, so we can modify it. If I'm going to modify it, I'm going to come here where it says edit simulation. If I'm going to create a new simulation for the AC sweep, I can do it here. So I'm going to edit the simulation. I'm going to keep the same simulation. It was DC sweep before. Now I'm going to make it AC sweep. And AC sweep usually is done as logarithmic, not linear. AC sweep basically stands for frequency response. And the reason you want to do it logarithmic is to be able to draw body plot, which is basically V out over VI. And since VI is AC voltage that reads 1, then V out is basically the frequency response V out over VI, because VI is 1 volt, right? So V out over VI is basically the frequency response. Or so you're going to start the beginning of the frequency. So we're going to say it is 1, and the end of the frequency, let's make it 10K. So 10K. I believe the 3 dB corner frequency here going to be around 100 Hertz. So we're going to find out when we do the simulation, but I believe it's going to be around 100 Hertz, a little bit less. Anyway, you're going to start the simulation at 1 Hertz and end the simulation at 10 kilohertz, and then the points per decade is basically the resolution, which means that how many iterations we are going to carry over 1 decade. 100 is a good number for this simple circuit. If you wanted a higher resolution, you can make 1,000. Let's make it 1,000. What the heck, my BC is kind of fast anyway. So that's what we have, and then we're going to do apply, and then that's it. We're going to say okay. So now we have remodified our simulation from DC sweep to AC sweep, and we have removed the probe on page 1, so nothing gonna be measured here. We're gonna add the probes here. So all what I'm gonna do is I'm gonna add the probe at the output, basically to say that we're gonna measure the output voltage as the input voltage will change on a logarithmic scale. What will change here is the frequency of the input voltage, not the magnitude. The magnitude is going to be constant at 1 volt, only the frequency changes. By changing the frequency, we know that the voltage across the capacitor is going to drop, because this circuit is a low pass filter. The low frequency content will have high impedance here, so you will have a higher voltage across the capacitor. As the frequency increases, the impedance of the capacitor becomes smaller, and if the impedance of the capacitor becomes smaller, then the voltage across the capacitor will be smaller. Basically, we are doing the frequency response. What's the response of the output as we change the frequency, right? So we're going to run the simulation. Again, simulation is very fast, and you can see that this is the gain when I hit 0.707. I'm gonna be somewhere around here. It's more around 50 Hertz, right? So yeah, of course, because I have to do the 2 by factor. This is in Hertz, not in radian per second. So more or less it's gonna be about 50 Hertz, right? That's the cutoff frequency. So this here is V out versus VI. So what I want to do is I want to make it body plot. I want to change this measurement to body plot. So I'm going to double click on this one where it says VC at node 1, and I wanted to change this. So I'm going to delete that, and I want to measure body plot. So to do body plot, I can do the dB. So that stands for dB. And then I'm gonna go back and say that it's gonna be VC. I'm gonna do dB of VC 1 at node 1. I can use cut and paste, or you can type it if you want it. So this is gonna measure what's the output over the input, because the input is 1 volt, it's basically the output, and then in dB. So when we do that, you can see that this is the dB scale where you're gonna have 20 dB per decade. So as you go, for example, from roughly around 500, right, that's negative 20 dB, at 5,000 it's going to be 40 dB. So it's clearly that the straight line here going to be negative 20 dB per decade, because there's a first order, and when you hit the negative 3 dB is somewhere around here. So this is 2, 3 is somewhere around here, roughly around the 50 hertz. So around 50 hertz more or less, you're going to have the negative 3 dB corner frequency, right? So in any case, this is the frequency response of a first order filter, right? And that's what we have. So you can also add plot if you want it. So we're gonna go to plot, and we're gonna add plot to window. So now we're gonna have 2 plots. I'm gonna come here and I will say select, and now I'm gonna add the phase. So this is the gain in dB. We're gonna add the phase. So I'm gonna now say trace, add trace, and we're gonna do the phase, and the phase have the symbol P. So this is the phase, and then we're gonna say what's the phase of the voltage across the capacitor. Again, you can either type it P of VC1 colon 1, or you can just cut and paste, and that's what I did. So you can see that this is a first order filter, starts from 0 degrees and will end up at a negative 90 degrees, and at 45 degrees, somewhere around here, this is 40, 45, somewhere around here, you should have the 3 dB frequency, which is somewhere around the 50 hertz, right? So that's basically consistent with it, and this is body plot where you have the magnitude in dB and the phase in degrees, and that's what we have here. So computer simulations basically here will tell you what's the frequency responses. Now we're gonna do a transient response. So there is 2 voltage sources I will apply for the transient response. So what I'm gonna do is I'm gonna come back to the same circuit. I will click on this AC voltage source, I will delete it, and now I'm gonna add the sine wave. So it says V sine source, that's the one I want. So I'm gonna click on it, and now we are going to enter the parameter values, or the parameters values for the sine wave. So I'm gonna click on the offset, and I'm gonna make sure that the offset is 0 volts. Basically the sine wave doesn't have any DC offset. And then we're gonna enter the amplitude. So I will make the amplitude to be 1 volt, and the frequency we're gonna make it 50 hertz. So that's the corner frequency where you're gonna have around the 45 degrees phase shift. And then the AC component gonna be 0. There is no small signal to it that you can have. You can use the sine wave voltage source in ORCAD to do both, to do transient and AC response. Basically, if you put the AC value here 1, you can do AC sweep, and at the same time you can do transient analysis and look at what's the response of the voltages. In any case, here we're gonna do a transient analysis or time domain response. So we are going to come back and re-edit our simulation. So instead of using AC sweep, we're gonna do time domain sweep. In the time domain sweep, we're gonna measure the end of time. So what's the end of time we're gonna have? This is roughly around 50 hertz. So 50 hertz is roughly around 20 milliseconds. So we can show 5 cycles basically by saying that the simulation will run for 0.1 second. You have to do some calculations when the simulation will stop. Run to time, basically stop time, t-stop. So we're gonna run it for 0.1 second. That will give us around 5 cycles at 50 hertz. If you change the frequency here, you have to change the time here. The higher the frequency here, the smaller the time to show more details, or you have to zoom in. Another important parameter here is the maximum step size. So you want to make this smaller to have a higher resolution. I will make it 10 micro is good enough for the 50 hertz. 20 micro is also valid. 10-20 micro is good for 50-60 hertz kind of signals. So we're gonna say apply, then OK. So basically we defined the simulation type, which is going to be transient simulation. Now we are going to also measure VI, which is V2 here, and V out, the voltage across the capacitor. When we run the simulation here, we're gonna show what's VI is and what's V out is. And now we're gonna run the simulation. The simulation might take some time. It's actually fast. So you can see that we have 1, 2, 3, 4, 5 cycles. They are nice sine waves because the resolution of the sine wave is around 10 microsecond. And that is good enough. And you can see that there is a phase difference between them, right? It's about 45 degrees. So if you come, forget the first cycle because you have some initial conditions, but if you come around here, you can see that the phase is roughly around 45 degrees, and V out is roughly around 0.707 or 0.71 of VI, right? So the magnitude shows you that this is around the corner frequency, phase shift of 45 degrees, and the magnitude drops by 3 dB, which is 1 over square root of 2 of the peak value. So if the peak value is 1, this is going to be 1 over square root of 2, which is roughly around 0.71 times the 1, right? If this was 2 volts, it's going to be 0.707 times 2, so that would be roughly around 1.4 or 1.45 more or less. In any case, what you did here is you showed the time domain response, the transient response of a sine wave, right? Which makes sense, right? This is a low pass filter. In fact, that if we increase the frequency, you're going to see that the output voltage will drop. And let's do that, and let's increase the frequency. So now we're going to come to the sine wave, and the frequency, we're going to increase it by a decade. So we're going to say that it is 500, so we increased the frequency by a factor of 10, and I'm going to come to the simulation, and I'm going to reduce the simulation time by a factor of 10, so it's going to be 0.1 seconds, and here we're going to say that the resolution is going to be 1 microsecond at maximum. We're going to say apply, okay, we're going to measure VI versus V out, but the frequency now is 500. The frequency is higher. We would expect that the voltage across the capacitor is going to be smaller because this is a low pass filter. So let's run the simulation, and when you do that, you can see that the voltage dropped by a big factor, roughly 20 dB, right, more or less. So you know, that works according to what we stated, that this is a low pass filter. You can even increase the frequency by a factor of 10, and you're going to see the voltage going to even drop more. Let's do that one more time for the heck of it to show you how easy it is to run the simulation. So we're going to come here, and we're going to say that the frequency going to increase to 5000. This is for the sine wave. I'm going to come to the simulation. I'm going to re-edit the simulation. I'm going to reduce this by a factor of 10. So if it is going to run to 1 millisecond, right? And here we're going to say that the resolution going to be 0.1 micro. Basically drop it by a factor of 10. Apply. Okay. We're going to measure V out versus VI. You're going to see that V out going to be much smaller by another factor of 10. So let's run the simulation, and you should see that the voltage dropped even smaller, right? So much smaller, right? So it drops by a factor of 10. So indeed that this is a low pass filter. By increasing the frequency, the voltage will drop. This here is called transient analysis. Apply the sine wave, and we were looking at V out versus VI as a function of time. Now for completion, I'm gonna add a rectangular pulse here. So a rectangular pulse will show you what is the time required for the voltage to reach its final value, as the input voltage will go from 0 to 1, and if it goes from 1 to 0, it will show you the time required to drop down to its final value. Now this is also another important concept. So in order for us to do that, we're going to add another voltage source. We're going to call it V pulse. So we have it here. So V pulse is in the source library. Double click on it, and we're going to place it here. Then click escape to cancel the extra voltage sources. We have a lot of parameters here we need to add, so we have to be careful to what we add. The first value here will be V1. That's going to be what's the initial voltage that you're going to have for the rectangular pulse. The rectangular pulse will continue generating voltages as rectangular waves forever, right? So we call them rectangular pulse. We're going to start with a value 0, so let's make sure that the first value, initial value, is 0. The second value, it's going to go to 1 volt. So this is in a way a unit step function. It goes from 0 to 1, and we're going to start this at some time TD, when the first initial step will jump. So we can say that this is going to start at let's have a good number. We can always start at 0, but let's give it some delay. So I'm going to say we're going to delay it 10 milliseconds. So 10 milliseconds, that's the time of delay we're going to have. And the time rise for the rectangular pulse, you cannot make the time rise instantaneous. This becomes a discontinuous function. Computer simulations don't like that. So when you jump from 0 to 1, what's the time required? We're going to make it very small, like 1 micro. You can make it 1 nano if you want it. 1 micro is good enough for our simulation here. The reason is the pulse width and the period of the rectangular pulse is going to be much higher than that. So 1 micro is going to be okay. The time fall, we're going to make it also another 1 micro. So 1 U stands for 1 micro. Now the period, the pulse width is for how long the pulse gonna go from when it jumps from 0 to 1, for how long is it gonna be? So we're gonna say that this is gonna be roughly for 20 milli, and then the entire period gonna be 40 milli. So here, what are the information that we did say is that, let's go back, I think there's something is missing here. At V1, we're going to initiate it to be 0. And for V2, we're going to make it 1 volt. So basically, if you look into the parameters, let me zoom in here a little bit so you can see it. If I zoom in into those parameters and show you what we have. So V1 is the initial value of the rectangular pulse, going to be at 0. It's going to jump to 1 after some delay time of 10 milliseconds. So it's not going to do the jump until it hits 10 milliseconds. And when it jumps from 0 to 1 volt, it's going to require you 1 microsecond. Something happens fast. And it's going to stay 1 for a pulse width of 20 milliseconds, and then it's going to jump down to 0, and the time required to jump down to 0 or to fall to 0 is 1 microsecond. So you can see that it jumps down very fast compared to the 20 millisecond. The period is how long will it take to repeat the whole process again, will be 40 milliseconds. So every 40 milliseconds you're going to have the same repetitive process. So we're gonna do this simulation. So we're gonna define a new parameters for the transient analysis. Now again, this is also a transient analysis response, so you want to plot things as a function of time. So the end time here gonna make it 120 millisecond, basically gonna take 3 times of that rectangular pulse, and the resolution we're gonna make it maximum resolution, we're going to make it 1 micro. When it comes around the time fall and the time rise, where it happens very fast, this resolution going to be smaller. So the maximum step size, so this is kind of automatic algorithm, the maximum step size is going to be 1 micro. But if the circuit requires you to go into smaller resolution because you have like sharp abruptions or sudden change in the values, the simulation automatically will slow down and have a finer resolution than the maximum step size of 1 micro. So that's something you have to keep in mind as you start to simulate more complex circuits. But for now, this should work and that should be good enough. So keep in mind that simple RC circuits are very fast to simulate and they are introductory level circuits. So this particular circuit will run very fast. Again, we're going to plot the voltage across the capacitor versus VI, and the voltage across the capacitor is going to have the green color. This is going to have the red color. I believe that's what we're going to have. Let's run the simulation, and now we see what we have. So already done. So let's look at the simulation. Voila, that's what you have. Beautiful RC circuit. So there is some delay for the jump to happen at 10 milliseconds. The input voltage changed from 0 to 1. The voltage across the capacitor will have some time to reach the final value. So you can see that the time required is kind of long. Usually it is 5 times tau, right? 5 times tau is the time when you reach the final value. We call it settling time, right? Anyway, so you have different parameters to measure the time rise and the time falls, and so you can see that you almost reaching the final value. This is not 5 tau, 20 milliseconds, not 5 tau, it's much less than that. So anyway, that's what you have. And then when it drops slow, from 1 to 0 volt, the voltage across the capacitor will have some time to reach the final value. So, and that's the end of the simulation. So in summary, to summarize what we did, we said that we installed ORCAD. ORCAD is a very powerful tool to simulate the circuits and dump the circuits into PCB design. But to do that, you have to learn how to use the ORCAD and to simulate the circuits. Basically, simulating the circuits requires you to do different kind of analysis. The most 3 common analysis that we use at the introductory levels are DC analysis, small signal AC analysis, and transient analysis. There is other analysis that are extremely important in the industry. One of them is the Monte Carlo. So Monte Carlo analysis basically will say that if, for example, this resistor changes by 20%, what's the performance of V out gonna be, right? Because you're gonna have some statistical deviation for R4 and C1, right? And maybe even the values of the input voltage. It's not always gonna go from 0 to 1. It's gonna go from 0 to 1, but the one gonna have plus or minus 10%. This resistor can have 5%. This tolerance, this capacitor can have 20% tolerance. So you have to run some statistical analysis, and one of them will be the Monte Carlo analysis. That is extremely important. Another one is temperature sweep. Many electronic circuits will vary with temperature. You can do that. There is another one in the AC sweep is called noise. So we need to have noise analysis to run the frequency. So you can do noise analysis, and to do noise analysis you can come here and you can run also noise sweep. Now those things also you can learn when you get to learn advanced topics in electrical engineering. Noise is extremely important. So those are very powerful software packages that engineers use, and it helps them to develop successful PCB application circuits, and it is industry standard software. So I hope that this tutorial helped you, and hopefully you can move forward from this simple tutorial.